name is Shannon Colton. I'm the director of the Smart Team program. Today we're going to hear from the Smart Teams, but before we get into their presentations, I wanted to give a background of the Smart Team program and just sort of an overview as to what the students have been working on for the last 6 months or so. And I would like to point out that this is the 10th year of Smart Teams. This has been a really wonderful experience that we've been able to offer to schools for the last 10 years. So Smart Teams began in the summer of 2001 with a group of high school teachers who came in and learned about the program and modeling and exploring a different topic and working with the researcher. And this group of teachers actually modeled a ribosome, which is involved in translation, and the ribosome was the subject matter of the Nobel Prize a few years ago. So Tom Stites won the Nobel Prize for his exploration of the ribosome. And Tom Stites is actually a former resident of Wauwatosa, so we kind of claim him as our person. So he helped us through Smart Teams. He got a Nobel Prize. Man, wonderful. So of these 6 teachers here, they enjoyed the process so much that they felt like they needed to take it to their schools and their students and give them the opportunity to explore modeling in the same way. And so in the fall of 2001, we had our very first Smart Team. And this was a team called Team Anthrax. And these students were modeling proteins involved with anthrax. So if you go back in our history now, about 10 years, fall of 2001, this was about the time that anthrax was being mailed through the postal system. So it was a very timely topic for these students to undertake. And in fact, several of the models that the Smart Team designed were taken to a congressional hearing. And they were the people walking into the congressional hearing had boxes labeled anthrax on it. It's very interesting that they actually were able to get into the congressional hearings in light of everything that was happening. So from that one team of 3 students in 2001, we now have over 60 Smart Teams participating in the program nationwide. And so we have a variety of different types of teams, and we do have one up in Canada, so my little red star that's up there floating, it's not floating, it's in Canada. A few years ago, we received a grant from the Howard Hughes Medical Institute to disseminate this program. And so all the blue stars represent partners in that program where they essentially replicate the program as we do it at their site. So there's a Shannon there running the program the same way that we do here. The little red stars indicate teachers who have come to our professional development course during the summer, learned about Smart Teams, very excited about this opportunity, and went back to their school and hosted a Smart Team at their school. And they do most of their correspondence with me, and some of them have found researchers in the area that they work with. Others just work directly with me during the course of the year. So you can see we've got about 60 teams spread across the U.S., and it's been a really nice growth to go from that single team 10 years ago to now we have over 60 present. So I have to acknowledge a few people as we go through this presentation. The teachers who run the program at their school are amazing people. There's no way we would be able to do the Smart Team program without the dedication and perseverance that these teachers show. So I'm going to run through this list. I know it's a long list, but I want the people who are here during this session to stand up, and then we're going to give you guys a nice big round of applause at the end. Okay, so Jean Lee from Bradford High School, Louise Thompson from the Brookfield Central School, Jana Vogt from Brown Deere High School, Karen Tiffany from Cedarburg High School, Dan Kozlkiewicz from Cudahy High School, Dan Getz from Grafton, Julie Fangman and Martin Bolt from Greenfield High School, Steve Plum from Kettle, Moraine High School, Jody Garg from Laconia, Keith Konstanski, Mike Cabrero, and David Vogt from Marquette University High School, Carol Johnson from Mesmer High School, Kevin Kopacki from Milwaukee Academy of Science, Sue Gepsel and Ann John from Nathan Hale High School, Donald Flom from St. Dominic Middle School, Cindy McLinn from the St. Joan Antietam High School, Joe Fincher from Valdez High School, Marianne Hosch and Peter Vendezan from Wauwatosa West High School, Paula Kukar and Michael Crack from Whitefish Bay High School, and Trish Rofel from Wisconsin Virtual Learning. These people are amazing and deserve a great job. Mentors who also give of their time generously, so I'd like to acknowledge them in the same fashion. So if you are here, I'm going to run through the names, you guys can just stand up too. Abba Upadavia and Dina Hammond from the University of Wisconsin-Milwaukee, Madhu Day from the University of Wisconsin-Milwaukee, Cecilia Hillard and Lalitha Cheta from the Medical College, Tin Fen Yang from Marquette University, Andrea Ferrante from the Blood Center, Ryan Rhodes from UWM, Shama Mirza from the Medical College, Jim Fikes from the Medical College, Deb Newman and Ben Trudeau from the Blood Center, Wei Kwok and Yifan Zhao from the Medical College, Dan Sam from Marquette University, Sarah Kohler and Penji Lee from the Medical College, Nancy Downs from the Medical College, Jason Bader from the Medical College, Sally Twining and Emily Andrea from the Medical College, William Jackson from the Medical College, Ed Blumenthal from Marquette, Gil White and Jackie Coyle from the Blood Center, and Kirsten Yanish from the Medical College. Again, these people are a wonderful addition to our program. Thank you. So we're running the Smart Team program. We have a few objectives that we'd like to accomplish during the course of the year. One of which is to experience science as a dynamic process. All too often we've seen students look into a science class and they see that the textbook's this big and it's this big giant list of facts that they have to memorize, and it's not fun, it's not engaging, nobody wants to just memorize facts. Unfortunately, that's the way science is presented in a lot of classrooms. I know it's not your classroom, that's just not how it works for you, but what we want the students to see is that science is a dynamic process in the sense that it's active, it's a research process, people are asking questions, they're doing experiments, they're coming up with some data and conclusion that eventually become those facts that you see in the textbook. So there is a process to what they see. We want the students to engage in modeling practices. So when researchers are designing their experiments or trying to lay out what it is that they're going to be doing, they have a model of what they envision the actual process to be. So they might have a sketch, they might be able to draw it out for you, they might be able to just verbalize it, but they have a model of how they think their particular protein is working within the cell. We want the students to get involved in that process. So understanding that model, working with physical models themselves, kind of getting at it from different sides. We want them to learn some technology. So for many of them, visualizing protein through JMOL is a new experience. Maybe even developing a poster through PowerPoint might be a new experience. So this technology is a set of skills that will move beyond the Smart Team experience. They're going to explore particular research topics. This is whatever their mentor has elected them to model during the course of the year. And they're going to develop communication skills and practice working as a team. So regardless of what career students may choose, whether it's science or anything along those lines, they're still going to have to work with other people and they're still going to have to find a way to communicate. So by setting it up in this way, the students have a chance to work as a team and they work on presenting their materials. So this gives them an opportunity to practice those skills to take with them in their next level of education or career. The Smart Team program itself is divided into 3 different phases: the qualification phase, the research and design phase, and the presentation phase. So the qualification phase begins in the fall, mid-September. The students come to the Milwaukee School of Engineering and we learn about basic biochemistry concepts that are involved in proteins. They do this all very early on a Saturday morning. And so what we do is basically throw at them a bunch of models and get them exploring protein biochemistry, starting with water and properties that water has and how that may influence folding, amino acids and how those amino acids come together to make a full protein, how those proteins then fold up to adopt their final shape in order to be a functional protein of the cell. So in addition to having to do all of this modeling, we talk a lot about what science is, whether it's a dynamic process. I also have them writing a lot, and we start talking about how abstracts are written and how you communicate science. So it's a very busy 3 hours that first Saturday morning. And essentially it's there to help sort of lay the foundation for the remainder of the program. So the next meeting that we have, the students actually come here to the medical college. We use their computer lab up on the 3rd floor. And we start talking about how do you design a molecule using JMOL, which is our computer visualization program. So the students, because of the fact that that's a 100 computer lab environment, I can put students at a computer and actually sit down and start talking about design work. So we go through a process and design models and get them comfortable with that. At that point, I give them a qualification challenge where they need to go back, write an abstract, and design a model. And this year we chose the OpC-A protein, which is involved in bacterial meningitis. So the students put that together as a way to practice their technology prior to meeting with their mentor. The 3rd Saturday that we meet, we have our qualification exam, in which the students come to MSOE. I shower them with lots and lots of questions, ranging from what product is produced after the catalytic reaction of putting together 2 amino acids, to how do you design a certain part of a molecule in JMOL. I also asked some questions about what was the Packers score last weekend, or the next Harry Potter movie to be released. So kind of running from the gamut of all the protein biochemistry, JMOL, we asked questions about the specific topics that they've learned. Notice the smiling faces. They're enjoying themselves, even though they are being submitted to the application exam. All right, so for my students.
Jack Sparrow.
Jack Sparrow. Captain Jack Sparrow. So lots of questions. So we kicked off the research and design phase of our program by having a mentor match. We bring in all of our mentors and all of our SMART teams, and we do sort of a speed dating round where the teams are all at their tables and the mentors rotate around and visit each team. The students ask the mentors questions, the mentors ask the students questions, and the goal here is for our students to see that researchers have lives outside of their labs, hopefully. So they enjoy going on vacations or going to see movies or spending time with family. And so we just want them to see them as real people. After the speed dating, we had a little competition to see who learned more, the students about the mentors or the mentors about the students. After we have this little fun competition, I match the teams up with their mentors, and then they start the conversation with their mentor about whatever particular protein they're going to be modeling for that time. So for the next month or two, they work very closely with their mentor and design a model of their protein. We get those files submitted to us mid-December, and then so on our meeting in January, we kick off our presentation phase, and they get their copies of their models that they've worked on to build. And then they use these models to start talking about how they're going to communicate their molecular story. Science is done in the lab, but it can't be done in isolation of everybody else. You have to be able to communicate your science out there so that if you find a cure for cancer, you tell people so they can implement it and do something with it. So the presentation phase is designed to have the students communicate their projects in two different formats: a poster and an oral presentation. So on this day, we have the mentors join the students after they've kind of gotten some information about the two different types of presentation. And they start to work on laying out how they're going to tell their story in a poster format and how they're going to tell their story in an oral presentation format. So during the months of January and February and early parts of March, they were designing these different presentation formats. So last Friday, the students down the hall from here put together or did their presentations on their poster boards. And so at this time, there was an opportunity for the students to communicate their project to a very scientific audience. We had a lot of PIs and the research labs come down, grad students, postdocs, fellow students. And it gave the students a chance to communicate their science in a very scientific way, in the sense that their audience was knowledgeable about a particular field. So we wanted them to be able to communicate that story and use their tools, their models, their posters, and tell the story of what they've been working on for the last few months. And it was a very packed house this year. We had a great turnout. It was very nice to see. At one point, we couldn't really even walk down the aisle between the posters. There were so many people. So it was a really nice session. So after the poster session, the next format that they were doing was the oral presentations, which we're going to hear today. The oral presentations are designed to be for more of a lay audience. So the point being here is that you have to be able to communicate the story in multiple different ways. So without further ado, I'm going to turn this over to the SMART teams, who are really the people who should be presenting. And so I'd like to bring up the Kettle Moraine team. They're our first to present this morning.
Hello and good morning. My name is Samantha Sinek, and I'm a senior at Kettle Moraine High School, and I'm proud to introduce the Kettle Moraine SMART team. This year we explored the protein patatin. Patatin is a specific protein found in potatoes that catalyzes the cleavage of fatty acids from membrane lipids. Proteins like patatin are known as phospholipases and have a variety of functions, including membrane remodeling, production of important signaling molecules, and digestion of dietary fat. Researchers are studying patatin currently in order to discover the structure of a similar phospholipase known as XOU, which is found in the bacteria P. aeruginosa. This is important because XOU is a protein used by P. aeruginosa to destroy cell membranes in vulnerable patients such as cystic fibrosis sufferers and burn victims. Researching patatin will lead to a better understanding of XOU and eventually new treatments to fight the harmful effects of P. aeruginosa infections. During our presentation today, we'll be focusing on the harmful effects that XOU has on cystic fibrosis sufferers and burn victims. Together, we will explore P. aeruginosa's destruction of cells with XOU and its ability to resist antibiotic treatment over time, and how new and improved ways of stopping the effects of P. aeruginosa will happen by targeting proteins like XOU. So first, we're going to discuss how P. aeruginosa infects the cell. The players of this infection include P. ruginosa, represented by Davy, and the virulence factor that P. ruginosa uses is XOU, which is represented by the sword she wields. And we have 3 different types of cells, represented by the people in blue t-shirts, that P. ruginosa infects. The villain in this infection is, of course, the evil bacteria P. ruginosa. The sword she has is the protein XOU, and a virulence factor is defined as a protein secreted that aids in the infection and survival of a bacteria. The phospholipase XOU is injected into the cells by a type 3 secretion system and destroys the cell membrane of the host cells it infects, causing cell death. So our first victim is a lung cell, and the infection of P. ruginosa in lung cells occurs to the favorable conditions created by the disease cystic fibrosis. Due to the increase of thick, sticky, honey-like mucus that develops in the lungs, it makes a perfect home for P. ruginosa to attack with its virulence factor, XOU. By destroying the cell membrane with XOU, P. ruginosa has killed the lung cell, and the infection will spread further. Another cell that P. ruginosa can destroy with XOU is the skin cell and burn victims. Burn victims are another vulnerable group because there's increased risk of infection created by the open wounds without the protective layer of intact skin. Just like in the lung cells, XOU is used to destroy the cell membrane of the skin cell. And lastly, P. ruginosa can kill white blood cells, the cells of the immune system that protect our bodies from disease. This destruction is especially evil. By destroying the cell membranes of white blood cells, or the defenders of the body is less capable of fighting off infection, allowing P. ruginosa's infection to spread more rapidly. Now I will show you what P. ruginosa will do to these cells. The most common method used is the distribution of antibiotics. However, there is a rising problem due to the use of antibiotics. Due to high population and rapid reproduction, the evolution of bacteria happens very quickly. When antibiotic X, we'll use for example, is used to kill or slow down a bacterial infection, many if not all the bacteria may be killed. However, sometimes there are bacteria that survive the antibiotics. These surviving bacteria carry a gene or set of genes that give it resistance to that particular drug. By reproduction of the new drug-resistant bacteria, those drug-resistant genes are passed down generation after generation, creating bacteria that are no longer affected by antibiotic X. This poses a problem, especially for vulnerable groups such as cystic fibrosis patients and burn victims who may be using antibiotics to treat bacterial infections. Let's see how resistance affects P. ruginosa over a 2-year cycle. We have the antibiotics penicillin, and penicillin is one of the first antibiotics ever used. In fact, P. ruginosa now is completely resistant to penicillin, and penicillin is effective against gram-positive bacterial infections and weakens the cell wall of the bacterium, causing the wall to tear itself apart. We also have ampicillin, and it is very similar in that it also affects the bacterium cell wall. By interfering with an enzyme needed by gram-positive and gram-negative bacteria, ampicillin inhibits the final stages of bacterial cell wall synthesis during binary fission, causing cell lysis or breakdown. And lastly, we have neomycin, which is mostly found in topical medications like the familiar Neosporin, and it affects the integrity of the bacterium cell wall by the formation of holes in the cell wall and a loss of normal permeability. This causes the unbinding of the bacterium cell wall, causing large sections to fall away. So we'll show you what happens when antibiotics are first used against P. ruginosa. antibiotics such as penicillin, ampicillin, and neomycin will have little effect on P. ruginosa. Due to the antibiotic resistance that has evolved against many antibiotics, researchers are looking into a different class of medicines that won't kill bacteria, but instead will focus on targeting the bacterial functions essential to infections, which we call virulence factors, which is also represented by the sword, which is XOU. The approach of targeting virulence factors, by targeting virulence factors, the toxins that cause host damage and disease has many advantages, such as increasing the amount of bacterial targets and decreasing drug resistance in bacteria. In P. ruginosa's case, the virulence factor worth stopping is, of course, the phospholipase XOU, which causes the destruction of the cell membrane. By sheathing the sword, this signifies some of the many ways that virulence inhibitors could stop XOU from damaging the human cells. By interfering with the delivery system of XOU into the cell, we can stop the harmful effects of XOU. Without XOU as a virulence factor, P. ruginosa can live in the body, but will not have the harmful effects. So in conclusion, I would just like to restate that by studying pitadin, it'll lead to better understanding of the phospholipase XOU, and that P. ruginosa, which infects the cell by XOU, causes cell death to the lung cells, skin cells, and white blood cells. The antibiotics used on P. ruginosa will eventually become resistant, and we will have to keep making newer antibiotics to stop the infections, and new medicines, which will target virulence factors, will help to stop this resistance. Thank you.
So I'd like to thank the Kettle Moraine team, and I hope that sword is not dead.